and how do we get this important raw materials for the ammonia production, that is nitrogen and hydrogen, how to get from the hydrocarbons we have seen. So today we will talk about the next production process. Also, I think I left in between where we need to talk about the uh, flow sheet. A quick discussion. Thank you. Someone has started the recording. So today we will discuss about the production of urea. What are all the details required for the construction of this process flow sheet? All the things I will highlight during this 1 hour. So urea was first synthesized in 1828 from ammonia and cyanic acid. Urea was first synthesized in 1828 using ammonia and cyanic acid, and urea was the first organic compound from an inorganic compounds. This is the first synthesis of an organic compound from the inorganic compounds. That is the beauty with this. In the current modern industries, urea is produced from ammonia and CO2 because there is a big issues in the production of cyanic acid. It is environmentally very hazardous process to produce cyanic acid. That's why in the most of the industries in the modern world using ammonia and CO2 to produce urea. Urea is important fertilizer. I have shown you earlier in the when I introduced fertilizers that in India we produce urea, predominantly urea, then diammonium phosphate, then some specialty fertilizers we produce. So today we will talk about production of urea, and urea is the first component produced, first organic compound produced from an inorganic component. So we already seen last class that ammonia is being produced from nitrogen and hydrogen, and nitrogen and hydrogen is coming from the either syngas, from the syngas, then we convert it to nitrogen hydrogen feed. The syngas is coming from the methane or any hydrocarbons. So I also talked about the production of syngas from methane and also from hydrocarbons either by steam reforming or partial oxidation. Both ways we can produce the syngas. So we also seen in the last class that CO2 is the byproduct of ammonia production process. CO2 is the byproduct of ammonia production process. So that CO2, the byproduct from the ammonia production process, is combined with ammonia that we can use to produce urea. Let us see quickly where is the CO2 byproduct. I'm sure you all remember this one, how to get this nitrogen hydrogen feed to the ammonia production process. So we are taking natural gas, methane. We are taking the natural gas, methane. Then methane contains, depends upon the source where you are extracting, it will have sulfur. So desulfurization of methane will be done. Then methane reacts with steam in the primary reformer. Then it will produce, the methane converts methane plus steam, H2O, converts and reacts, produces carbon monoxide and hydrogen, and some amount of CO2 also will produce. That is what happened in the primary reformer. In the secondary reformer, the syngas, which is coming from the primary reformer, is reacts with air. primarily in the air, the syngas reacts with oxygen because nitrogen is a not inert component. It won't react with carbon monoxide or hydrogen. So the carbon monoxide present in the stream 3 here, which reacts with oxygen here, and whatever carbon monoxide is there, that will be converted to CO2. Whatever carbon monoxide is there in the stream 3 reacts with oxygen coming from stream 4 and completely converts to carbon dioxide. So you will have, after the second reformer, you have hydrogen, carbon dioxide and nitrogen. I forgot to mention here. So we will have in the stream 5, if you see the number 5, the stream 5, we will have hydrogen, carbon dioxide and nitrogen. These three will be there predominantly. I have even showed you the composition in the last class. So the stream 5 goes to the absorber, where we wanted to separate carbon dioxide from hydrogen, nitrogen. We wanted to separate from carbon dioxide from hydrogen, nitrogen. So carbon dioxide can be easily absorbed by any alkali solvent. Carbon dioxide can be easily absorbed by using an alkali solvent. So if you pass this gas, hydrogen, CO2, nitrogen over this alkali solvent, the CO2 transfers from gas phase to the liquid phase. CO2 transfer from gas phase to the liquid phase. That way, from the absorber, we will get two streams come outside. One stream which contain solvent plus CO2, another stream which contain nitrogen and hydrogen. In the stream 6, often the nitrogen to hydrogen ratio will be 1:3. Nitrogen 1 mole, hydrogen 3 moles. That way, the stream 6 directly goes to the ammonia production process. The stream 6 directly goes to the ammonia production process. Here, whatever CO2 which is taken as, whatever CO2 which is absorbed, will be utilized for the urea production process. Because we can easily recover CO2 from the alkali solvents. So here also, for some reasons, if you want hydrogen gas as a fuel, if you want this hydrogen gas as a fuel, you can recover this hydrogen from the stream 6. You can recover this hydrogen from stream 6 because in the current generation, especially in the current last 6 months or so, Government of India highly focusing on hydrogen fuels. Even abroad countries, many countries, Australia, Europe, America, they are only using hydrogen-based fuels for the starting from street lamps to almost big usages. So if you want to recover hydrogen from the stream 6, we can use certain adsorption processes, and in the textbook which I given to you, the details are given. You may please read the hydrogen recovery from the purge gases or stream 6. So this is the overall process, starting from natural gas reforming to the final ammonia production this flow sheet contains. So natural gas, you can see the bottommost stream goes to this is the stream number 1. The first one is desulfurization is taking place. Then it goes to the primary reformer. Then it goes to the secondary reforming section. After that, CO2 removal. After that, we have the CO2 removal. Then, whatever nitrogen and hydrogen is coming, that goes to the reactor, then recycled. So this is the whatever explained in bits and pieces, all together is given as this flow sheet. So you may get confused if you see big flow sheet, but I have already explained into small pieces. If you understand that, that will be sufficient to understand this. So today I'll move on to the urea production. Today we'll move on to the urea production. I'm sure you already know the basic chemistry behind urea. In the urea production or urea reactions have two reactions. In the first reaction, 2 moles of ammonia reacts with carbon dioxide, which is a very fast reaction, almost quick reaction, and converts to the ammonium ammonium carbonate. Ammonium carbonate. This is this is an exothermic reaction. This is an exothermic reaction. So, in the last class, I have explained whenever we have an exothermic reaction, if it is a catalytic reaction, we need very high temperatures, like above 500 Kelvin. If it is not a catalytic reaction, we don't need to go high temperatures like 500 Kelvin or 700 Kelvin. Why we need to go catalytic reactions high temperature? Any guess from the students? Why we need to operate catalytic reactions at high temperature? Any guess from the students? I mentioned in the last class, but just want to see whether anyone understood or not.
To activate the catalyst.
Very good. To activate the catalyst. To activate the catalyst, we have to operate at high temperature. But here is a non-catalytic reaction. This is a non-catalytic reaction, so we don't need to go very high temperatures. Now, for exothermic reactions at high temperature, forward reaction favors or backward reaction favors? For exothermic reactions at high temperatures, forward reaction favors or backward reaction favors? Backward reaction favors. Thank you. So at high temperatures, backward reaction favors. So we need to operate as low temperatures as possible. So that means what? We need to remove the heat. We need intermediate cooling. So that's what the first reaction is telling us. First reaction is reversible reaction, and this is exothermic reaction, and this is a quick reaction. No catalyst is required, so we don't need any packed bed reactors or anything like that. So we need to operate low temperatures. To operate at low temperatures, we need to remove the heat, intermediate. We need intermediate cooling. That's what the first reaction is suggesting us. Now, ammonium carbonate dissociates into urea and water. Just give me 1 second, a lot of background. Sorry. The second reaction, ammonium carbonate, it dissociates into urea and water. Ammonium carbonate dissociates into urea and water. This is a slow reaction. And again, this is endothermic reaction. Now we can see the heat produced in the first reaction is 159. Heat required in the second reaction is 31.4. So we can say overall in the exothermic reaction, overall it is an exothermic reaction because the first one is dominating than second one. So whatever heat required for the second reaction, some amount can be utilized from the heat produced in the first reaction. So that way some amount of heat will be utilized for the second reaction, still some amount of heat has to be removed. So both are non-catalytic reactions. Both are non-catalytic and reversible reactions. Now, one important question one may come to anyone's mind, that you can see ammonium carbonate also contain nitrogen. So this can also be used possibly as a source of fertilizer. Why urea can be used as a fertilizer? Because urea contains nitrogen, and this is a solid at atmospheric conditions, and that can be dissolved in water. Upon dissolving, urea can release nitrogen. That's why urea can be used as a fertilizer. I repeat, urea is a solid at atmospheric conditions, and it can be easily dissolved in water. Upon dissolving in water, urea can release the nitrogen. That nitrogen can be absorbed by the plants for the plant's growth. That is why urea can be used as a fertilizer. Now, why can't we use ammonium carbonate? Because ammonium carbonate also contains nitrogen. That is also a solid particle at the room temperature, atmospheric condition, that also dissolves in water. But so, if ammonium carbonate can be used as a fertilizer, we don't need urea. We don't need the second reaction. So, what is the problem? What is the problem with another problem with ammonium carbonate? Another problem with ammonium carbonate is that ammonium carbonate is solid at atmospheric pressure, atmospheric temperature, and the volatility of the ammonium carbonate is very high. The volatility of ammonium carbonate is very high. It dissociates into ammonia and CO2. As soon as, if you leave it in the normal conditions, ammonium carbonate easily converts into ammonia and CO2. Ammonia and CO2. But we don't want ammonia and CO2. We wanted nitrogen to get released. We don't want it to convert back into ammonia and CO2. If ammonia is useful, then we could ever use ammonia itself as a fertilizer. But ammonia doesn't be useful because ammonia binds with hydrogen very strongly, and nitrogen will not be allowed to be transferred to the plant so easily. So ammonium carbonate, I have another reasons why we cannot use synthesis. I have also reasoned two other reasons why we cannot use ammonium carbonate as a fertilizer. So please understand that this is fast reaction, this is slow reaction. So ammonium carbonate dissociates into ammonia and CO2 at the normal pressure, normal temperature conditions, because ammonium carbonate is highly volatile. Ammonium carbonate is highly volatile. Now, there is another side reaction, possible side reaction. Here, ammonium carbonate can be converted to urea and water. There is another possible reaction, another side reaction that also possible is ammonium carbonate converts to birute and ammonia. Ammonium carbonate converts to birute and ammonia. This is also an endothermic reaction. So we wanted second reaction to happen. We wanted urea formation to happen. We don't want this side reaction to be happen. We don't want side reaction to happen. We don't want first reaction to happen. We wanted first reaction to happen, but we don't want backward reaction to be happen. So what to be done? Now what to be done to avoid the backward reaction of the first reaction, and we wanted to second reaction to be happen, and again we don't want third reaction to happen. So these three has to be taken care. In the urea reactor, we should avoid backward reaction of the first reaction, that is we don't want dissociation of ammonium carbonate into ammonia and CO2. So that's we don't want. We wanted forward reaction of second reaction, that is ammonium carbonate to convert it into urea and water. That's what we wanted. Again, we don't want ammonium carbonate converted into bioroot formation. So how to deal with this? Before this, the question comes, can we use ammonium carbonate as fertilizer? Answer is no. Why? It is a volatile component. It releases heat. It is a volatile component and it releases heat. If at all, if you put ammonium carbonate as a fertilizer, rather than utilization, it will burn the plants. It will burn the plants because it's a highly volatile component and dissociates into ammonia and CO2 and it releases heat. That heat basically burns the plants. So that's why ammonium carbonate cannot be used. What are the other problems with ammonium carbonate? Ammonium carbonate, as I said, first reaction that needs to be operated low temperatures because high temperatures favors the backward reaction. But what problem happens if you operate at low temperatures? Ammonium carbonate, it is a solid at atmospheric pressure and room temperature. It tend to form as a film if you operate the reactor below its melting point temperature. It tend to form as a film. The ammonium carbonate tend to form as a film if you operate the reactor below its melting point temperature. So that means although the first reaction to be operated at low temperature, but we cannot operate at very low temperatures. We cannot operate at very low temperatures. Why? If you operate very low temperature, that to below the melting point temperature of ammonium carbonate, the ammonium carbonate tend to form as a film. What is the problem with the film? The thermal conductivity of the film is very low. That means we cannot do the intermediate cooling. The efficiency of the intermediate cooling very low if the thermal conductivity is very low, and it is and that is why we cannot operate low temperature. But at the same time, if you operate very high temperatures, the ammonium carbonate acts as a highly corrosive agent. If you operate very high temperature, it will act as a highly corrosive agent. So we cannot do anyway at low temperatures. We have to do at high temperature. So to mitigate these corrosion problems, we need to use a proper construction material required for the reactor, ammonia reactor. The ammonia reactor needs to be constructed with a very special materials where it should have a very high corrosion resistance. So these are the solutions to these problems. Ammonium carbonate reaction, that is first reaction, although favorable at low temperatures, we cannot operate at very low temperatures. Why? If you operate at low temperatures, ammonium carbonate is tend to form as a film. What is the problem with that film? The thermal conductivity of the film is very low, hence it will not be helpful at all, or it will not be possible to remove the intermediate cooling. Now if you operate high temperatures, two problems: backward reaction favors, at the same time ammonia carbonate can be highly corrosive. So there has to be an optimum temperature. That needs to be run for the urea reactions. So how do we find out the optimum temperatures? Again, we'll go back to the thermodynamics. Study to find out the optimum temperature. So key factors to be maintained in the reactor is to avoid the dissociation of ammonium carbonate. Sorry, there is a typo here. R should not be there. A reactor needs to be operated at high pressure. To avoid the dissociation of ammonium carbonate, the reactor needs to be operated at high pressure. So since reaction will have an equilibrium conditions, that is at high temperature backward reaction favors, we need to remove the excess heat produced during the reaction. We need to remove the excess heat produced during the reaction that I already discussed. So this is from the kinetics point of view. I think first we will see this. So this is the thermodynamic point of view. So CO2 conversion in the liquid phase, that is ammonia react with CO2, both will happen in the liquid phase. Now we can see, now you can see that the optimum temperatures is around between 190 to 200. The optimum temperatures are between 190 to 200. We cannot operate it below 70, then conversion will be very, very low. We cannot operate it below 160 because the conversion will be very low. Again, we cannot operate it above 210 degrees centigrade because the backward reaction favors. The backward reaction favors. So this is from the thermodynamic equilibrium, thermodynamic studies, from the chemical thermodynamic equilibrium studies, which clearly indicates that it is very ideal to use between 190 to 200, but we can use between 170 to 200 conditions. So the normal urea reactors operates between 170 to 200 degrees centigrade. At this range, approximate CO2 conversion achieved is around 70%. The approximate CO2 conversion achieved is around 70%. So this is CO2 conversion to ammonium carbonate. Ammonium carbonate. So this ammonium carbonate to urea conversion. This graph, it tells us that ammonium carbonate to the urea conversion. So as I said, ammonium carbonate to urea conversion reaction is a slow reaction. So at what temperature, how much residence time we need to maintain, we can understand from this graph. At what temperatures, how much residence time we need to maintain, we can understand from this graph. So this graph also suggests that between 160 to 200 degrees centigrade, you can see here, if you operate at 145, with very, very slow reaction. So it's almost taking 3 hours. It's almost taking 3 hours to get approximate 40% conversion. But if you operate at 160 degrees centigrade, if you operate, it is endothermic reaction. That's why at higher temperature it is better. Higher temperature it operates better. At higher temperature it will operate better. So at 160 degrees centigrade, it requires almost 2 hours to get a stable conversion. But if you operate at 180 to 200 degrees centigrade, it requires much lower time, much less than 1 hour time to get the 60% conversion. So that means even from this graph, the favorable conditions are 100, 170, 200. Even from this, the favorable conditions are again 170, 200 condition. So even from the CO2 conversion to ammonium carbonate converts to urea, both showing that the temperature maintenance, the normal operating conditions has to be 170 to 200 degrees centigrade. Close to 200 is always better. Close to 200 is always better. And to avoid the dissociation of ammonium carbonate back to the ammonia and urea, we need to run at high pressures. So we operate 130 to 300 bar pressure. Now, at what ratio? Ideally, you can see here from the reactions, we wanted 2:1 ratio. Ideally, we wanted 2:1 ratio, right? Ideally, we wanted 2:1 ratio. Now, which is limiting reactant here? CO2 is the limiting reactant. Here, or usually in the urea reaction, CO2 is the CO2 conversion limits the reaction. So now, if you want to avoid the backward reaction, what we have to do? Can anyone guess? If I increase mole ratio or if I decrease mole ratio, I can avoid the backward reaction. Okay, let me say, here we need 2:1 ratio, but usually we operate at higher ratios. Usually we operate at higher ratios. NH ammonia to CO2 ratio, stoichiometric required ratio is 2, but we operate slightly higher than 2. We operate high at 3. We operate at a ratio of 3. The reason is, if I maintain ammonia in excess, if I maintain ammonia in excess, I can avoid the backward reaction. Also, I can avoid this Biroot reaction. Formation. So that is the reason. Another important thing we do is we input more amount of ammonia than stoichiometrically required ammonia. We input more ammonia than the stoichiometrically required ammonia. So from thermodynamics, from the kinetics point of view, we need to operate at 170 to 200 degrees centigrade and at this pressure. And to avoid this Biroot formation and to make the first reaction in the forward direction, we supply slightly excess ammonia than the stoichiometrically required ammonia. I hope students were able to understand. Okay. Since no comments, probably I assume that you all understand, be able to understand. Now, as we can see, this is non-catalytic reaction. This is a non-catalytic reaction. So this is a liquid phase reaction. Ammonia and CO2 is liquefied before we send to the reactor. What reactor can be used? Can any guess from the students? What reactor we can use? Reactants are in liquid phase, non-catalytic reaction, and that needs to be operated at 170 to 200 degrees centigrade and high pressure. What reactor is best in this case? What reactor do you suggest? Students, what reactor do you suggest? Okay, let me ask. What are the reactors available to us? Can anyone say? What are the reactors available to us from CRE or whatever I discussed in the unit operations, unit process class? What are the reactors available to us? First one is CSTR. Second one,
CFR.
PFR. These two are the used for what type of reactions? CSTR and PFR. For what reactions we use? Non-catalytic reactions, right? Simple CSTR, simple PFR used for the non-catalytic reactions. For catalytic reactions, solid catalytic reactions, what reactors we can use?
Packed bed.
Packed bed reactor, very good. And any other reactors? Fluidized bed reactor, packed bed reactor. Then we can also use slurry reactor. We can use trickle bed reactors. Those are the 4 catalytic reactors. We have only 6 reactors. Always remember, we have only these 6 varieties of reactors which we can use. For non-catalytic reactions, CSTR and PFR. Because just simple mixing of reactants. Now if we have liquid reactants and solid catalysts, we can construct reactor as a packed bed reactor or fluidized bed reactor. or slurry reactor or trickle bed reactor. Anyone remembered when do we use slurry reactor? Anyone remembers when do we use slurry reactor? I have discussed when do we use slurry reactor.
For non-porous particles.
Non-porous particles, and particles are very small.
Smalls.
Very good. Thank you so much. Slurry reactors are used if the catalyst is non-porous and very very small. When it is non-porous, it has to be, the particle size has to be very small. So there we use slurry reactor. Thank you. So here this is non-catalytic reactor. So what reactors we can use? What reactors we can use? This is non-catalytic reaction. Ammonia conversion is non-catalytic reaction. So what reactor we use? We have only two, right?
PFR or CST.
PFR or CST. So which one we prefer? PFR we prefer or CST we prefer? Or what is the basis? Now here what are the conditions? High pressure reactor. These are the high pressure reactors, right? So when you use high pressure and if we need to do intermediate cooling of PFR and CST, which is more preferred?
PFR.
PFR is more preferred. One more condition also required. PFR is more preferred where we don't need mechanical stirring. PFR is preferred when we want to, where we don't need external mechanical stirring. Now here CO2 and ammonia, liquid streams, both are, this is a liquid phase reaction, both are liquid streams. So by maintaining proper flow rates, we can easily mix them. We don't need an external mechanical stirring. So when we need external mechanical stirring, we prefer more CSTR. But when we don't need external mechanical stirring, then we prefer PFR. And high pressure reaction, intermediate cooling, first option is PFR, then second option is CSTR. So here we use a plug flow reactor. The urea reactor is a simple plug flow reactor. Plug flow reactor means simple tube, right? Simple tube. Simple tube it's not that simple because we are operating high pressure and we need a corrosion resistance material because ammonium carbonate can be highly corrosive. So those are special features are there. But just for visualize, the PFR is like a simple cylindrical tube. But now a simple cylindrical tube can be called as a pipe, can be called as a reactor. When we call as a reactor, if you maintain required pressure, required temperature, where the possible reaction can happen, then the same tube is called as a reactor only. The same tube is called as a reactor only. So here, this is a liquid phase reaction. So CO2, the CO2 has to be compressed. CO2 has to be compressed to high pressure to convert it into liquid. And ammonia, the ammonia which is liquid ammonia which is coming from the ammonia production process, and then both are directly introduced into the reactor. Both are directly introduced into this reactor. So liquid ammonia from the ammonia production process comes and pumped into the reactor. CO2 is compressed, liquefied and introduced into the reactor. So this reactor operates, as I said, 170 to 200 degrees centigrade and 130 to 300 bar pressure, right? By the time it comes here, what will be there? Urea will be there, unreacted ammonia will be there, unreacted CO2 will be there, and unreacted ammonium carbonate will be there, and water will be there. These four components will be there. After, in the stream leaving the urea reactor, 4 components will be there. Four components will be there. What will be there? Unreacted ammonia, unreacted CO2. Both are in liquid phase. Unreacted ammonium carbonate will be there, and urea will be there, and water will be there. So all these four components will be there. All these four components will be there. Now, from the thermodynamic data, we can see the conversion is around 70%. This is the conversion is around 70%. So now, whenever we have the conversion is less than 100%, whenever we have the conversion is less than 100%, what we need to do? What we need to do? Unreacted reactants needs to be separated. Unreacted reactants needs to be separated. Now, in addition to unreacted reactants, these two are the unreacted reactants. In addition to these, ammonium carbonate also there. In addition to these, ammonium carbonate is there. What is the pressure here? The pressure here, the stream leaving the pressure is around 140 bar. The pressure leaving this, the stream leaving the reactor is at 140 bar pressure. So how do we convert this carbonate into unreacted reactants? How do we convert this carbonate into unreacted reactants? So unreacted reactants are ammonia and CO2. How do we convert? Any guess from the students? How do we convert ammonium carbonate into ammonia and CO2? I gave a hint. I gave a hint already. How do we convert ammonium carbonate into ammonia and CO2? Yeah, ammonium carbonate dissociates at atmospheric pressure. Ammonium carbonate dissociates into ammonium and CO2 at the atmospheric pressure. Yeah, you can see here. Ammonium carbonate is solid at atmospheric pressure room temperature, volatility is high, and easily dissociates into ammonia and CO2. So, how do we convert this unreacted carbonate into ammonia and CO2? By releasing the pressure. So, at this point, the pressure leaving the reactor is at 100 bar pressure, 140 bar pressure. If we reduce the pressure from 140 to atmospheric pressure by using a pressure reducing valve, by using an expansion valve. But here this expansion valve is very special. We will not reduce pressure from 140 to 2 atmospheric suddenly. If you reduce suddenly, very high amount of mist formation will be there, very high amount of Byrite formation will be there. So that's why the pressure has to be released very slowly, gradually. So that's why they use very controlled pressure releasing valve called expansion valve. Very controlled pressure releasing expansion valve is used. While this urea is stable product, once it's converted to urea, it will not dissociate. It will not dissociate into ammonia and CO2. Only carbonate can be easily dissociated. So after releasing this pressure, the stream will contain urea, the stream will contain ammonia, and stream will contain CO2, and we have water. Now you know at atmospheric pressure, atmospheric temperature, urea will be in the liquid form. Of course, here still we haven't reduced the temperature. So at atmospheric pressure, atmospheric temperature, urea will be in the solid form. But at 450 Kelvin, urea will be in the liquid form. Since the pressure is atmospheric pressure, ammonia will be in the gas form and CO2 will be in the gas form. So since we have these two are gases and this is liquid, we can easily separate gas and liquid. We can easily separate gas and liquid. We can easily separate the gas and liquid. And these unreacted reactants can easily recycle back. The gases, ammonia and CO2, can be easily recycled back because they are becoming turned from liquid state to the gaseous state, and urea in the liquid state, water in the liquid state. We can easily separate gases from the liquid. So the separated gases can be recycled back. So this is the process flow sheet. This is the process flow sheet. So you can see here ammonia liquid ammonia from the ammonia production process is pumped into urea reactor. CO2 is compressed and sent as a liquid to the urea reactor. Now, these reactors operate at 140 bar pressure and 170 to 200 degrees centigrade. After the reaction, we use expansion valve. This expansion valve gradually reduces the pressure. So instead of straight away going to the 1 bar pressure, using this expansion valve, 140 bar to 20 bar pressure is reduced. 140 bar to 20 bar pressure is reduced. Then it introduced into the empty chamber. So once you introduce empty chamber, this ammonia and CO2, which is in a gaseous form, they will come out. Then we need to always heat the liquid because we wanted urea to be in the liquid form. So some amount of heating will be there. Then again, the pressure is reduced from 20 bar to 1 bar pressure, so that further unconverted ammonium carbonate further dissociates into ammonia and CO2. So that way, all the ammonia and CO2 is removed by gradually reducing the pressure. Again, we provide some heat here because while reducing pressure, there is a chance of urea to form the granules. Because urea is a solid at atmospheric pressure, at atmospheric temperature. So again, we are doing some amount of heat so that the urea will be in the liquid form. So this is an evaporative system. We are evaporating the gases, we are releasing gases at the same time. This is only here we have this expansion valve to reduce pressure, this further reducing pressure and further reducing the pressure. Then it goes to the vacuum evaporator. The vacuum evaporator is used to make sure that all the urea is at the required temperature. All the urea in the liquid form and no water is there. Only liquid urea is there. To produce that liquid urea, we are using the vacuum evaporator. You can see this is a molten tank. So just only concentrated urea in the liquid form. Now we wanted urea to convert it to the granules. So to convert urea into granules, here we use prilling tower. So let me explain this prilling tower, how this prilling tower operates. So this is the prilling tower. This almost looks like a cooling tower only. So this is a small tower. Now from the bottom, we introduce cold air. From the bottom, we introduce cold air. So the air is basically passing through. From the bottom. Now at the top, this is like a disc, cylindrical disc with some width. It's like a disc with some width. This disc has small holes. These holes are fitted with a nozzles. This is the hole and fitted with a nozzle like this, just like a shower, right? We all use shower. You can see this is a water shower with a what we call, we have like a disc type of thing, and it has a nozzles. It has a nozzles. If you operate, if you operate the shower at low flow rates, you can see a droplets of water falls. If you operate the shower at low velocities or required velocities, we can get drop by drop. We can get drop by drop. Exactly similar thing in the cooling tower. So we have the molten urea, the liquid urea is coming, and you have a nozzle here. We have nozzle exactly like a shower, disc with nozzles. Through these nozzles, we can see a droplets of urea comes down. The droplets of urea falls down. This is a liquid droplet. Now, as the droplet falls down, this is surrounded with a cold air. This is surrounded with a cold air. This is surrounded with a cold air. So, while this droplet comes in contact with cold air, what will happen? The molten urea, liquid urea at very high temperature, right? And air is at low temperature. Heat transfer takes place from liquid urea to air. That way, the urea droplets gets cooled down. So this is atmospheric pressure, and the temperature of the droplet is reducing. And while the temperature of droplet is reducing, the urea becomes solidified. Now we maintain air such a way that it will have a gradually settle. It will gradually settle, and it won't that the particle suddenly it won't fall down. We maintain the droplet size, air flow rate such that the particle gradually settles. The particles gradually settle. The urea granules gradually settle, so that you will have a less attrition between the particles will take place. So the design air flow rate, the droplet size such that it will get cooled down. Also, the settling behavior can be very gradual rather than just falling from the top. So that way we can avoid the attrition. So this is called filling tower. So that filling tower is used to form the urea granules. Now here, so that way we get the solid urea granules. They are packed and sent to the storage, then sells to the whatever farmers required. Now important question comes here is, can we recycle this unreacted ammonia and CO2? Can we recycle? The problem is, if you wanted to recycle ammonia and CO2 needs to be pressurized, because here the CO2 is pressurized to go into liquid CO2, and ammonia is also needs to be pressurized because ammonia has to be sent as a liquid. Now, if you individually separately pressurize them, no problem. But if you pressurize them, ammonia CO2 together, there is a high chance of carbamate crystals to form. It will convert it to carbamate. Ammonia reacts with CO2, forms carbamate. But if you pressurize together, there is a high chance of carbamate crystals formation. So one way is, since it's already 70% conversion, if there's utility, they will separate CO2 and ammonia. Then we have to separate CO2 from ammonia before you compress them. Or there is another way that I will discuss, because it's already 11 o'clock. So that we will discuss in the next class. So this is the typical reactor, CO2 stripping reactor, and as I said, plug flow reactor type use. We'll continue from here in the next class. It's already 11 o'clock. How to recycle? What is the way to recycle? That we will see in the next class. Thank you, students. If you got any questions, you may ask me. Otherwise,